The number e shows up everywhere. You calculate compound interest, you use e. You map population growth or sketch out probability bell curves, and e is there, perfectly describing the rate of continuous change. But in rigorous mathematical analysis, we don't start with continuous compounding. Walter Rudin defines e entirely differently, as an infinite series of reciprocal factorials. If we write this out, it starts with 1 plus 1 plus 1 over 2 factorial, which is a half, then 1 over 3 factorial, which is a sixth, then 24th, and so on. To know this sum actually results in a specific finite number, we compare it to a simple geometric series, 1 plus a half plus a quarter plus an eighth. By the fourth term, the denominators in our factorial series are growing much faster than the powers of 2. Because of this, the entire factorial series is strictly less than 3. Because the denominators multiply out so quickly, the series converges rapidly. We have a solid, bounded value to work with, making this infinite series the perfect starting point for rigorously proving everything else about e. If you open a standard calculus textbook, you'll see a different definition. The limit as n approaches infinity of 1 plus 1 over n, all raised to the power of n. We need to prove this limit is exactly equal to our factorial series. Let's call this limit sequence t sub n. Using the binomial theorem, we can expand it out. When we do, we get a polynomial made up of factorials multiplied by these distinct fractional parts, 1 minus 1 over n, 1 minus 2 over n, and so forth. Let's place our original factorial sequence, s sub n, right above it. Notice that all those fractional parts in t sub n are strictly less than 1. This means every individual term in our limit sequence is smaller than or equal to the corresponding term in our factorial sequence, so the upper limit of t sub n cannot exceed e. Now for the lower bound. We freeze a specific number of terms, let's call it m. As we let n grow toward infinity, the fractions like 1 over n shrink to 0. The terms in parentheses collapse into ones. Our frozen m terms of the factorial series are now less than or equal to the lower limit of t sub n. If we let m go to infinity, our lower bound rises up to match the upper bound. The limit is squeezed perfectly between them. We have proven that the textbook limit and Rudin's factorial series are the exact same value. Because the series converges so rapidly, we can calculate precisely how close finite terms get us to the true value of e. We do this by looking at the remainder, the difference between the true value e and our partial sum, s sub n. The remainder is simply the infinite tail of the series we haven't added yet. To simplify it, we can pull out the very first term of that tail, 1 over n plus 1 factorial. What's left inside the brackets is smaller than a standard geometric series. When we sum that geometric series, the entire expression condenses. The distance between our partial sum and the true value of e is strictly less than 1 over n factorial times n. This error bound is remarkably tight. Take a moment and think about the algebra we just established. If e happened to be a simple fraction, this strict inequality is about to break the rules of basic arithmetic. We will use that exact error bound to prove that e is irrational. We start with a classic proof by contradiction. Let's assume e is a rational number, represented by the integer p divided by the integer q. We take our error bound from the previous step and replace the variable n with our new denominator q. At the top, we keep our assumption clear, e equals p over q. To clear out the complex fractions, we multiply the entire inequality by q factorial. On the far right side, the q factorial in the numerator cancels with the 1 in the denominator. We are left with just 1 over q. Now look at the middle term. If we distribute the q factorial, the first part is q factorial times p over q, which is an integer. The second part is q factorial times our partial sum, which is also an integer. Subtract an integer from an integer, and the result must be an integer. But look at what we've built. The left side is strictly greater than 0. The right side is 1 over q. Since q is a positive integer, the right side is at most 1. We have mathematically trapped an integer strictly between 0 and 1. That is impossible. Our initial assumption must be false. The number e cannot be written as a fraction. By starting with a simple series of factorials, we confirmed the classic limit of continuous growth and proved beyond a doubt that e is irrational. If you want to master the proofs behind the math you use every day, grab a pencil and start expanding these series yourself.